Perfect. Okay, excellent. So you should, yeah, my screen is there. So yeah, today's session, we will have like three parts. One part we are going to make a quick discussion about deep learning, just to I know that most of you are already familiar with some of the concepts. Probably some of you are also familiar with the details, and probably some of you are already experts. Okay, so but the focus today is really to how to apply deep learning to network science, and in particular we are going to talk about graph neural networks. But I think it's good idea to start talking a little bit about the generalities of this topic, and how a graph neural networks are like a part of all these body of knowledge that is and we which is also growing very fast, which is now deep learning. Okay, okay, so I will start. Also, you were supposed to review some of the material, because the last part, okay, the first part is this discussion about general about deep learning, and then we are going also to discuss a little bit about the material that you have to review. And the second part, we are going to talk about how to deal with graph data using neural networks, and in particular deep neural networks. And the last part is going to be a hands-on, a kind of a workshop. So the idea is that we will work together to build a model, or actually a couple of models. So that part is going to be more interactive, and that's why I asked you to get familiar with TensorFlow, the and Keras. I know that it's a short time, but at least to get a general idea of how to use these tools. Okay, so deep learning. So the first thing about deep learning that okay, I will skip this. That I want to highlight is that despite the fact that this is like a hot topics now, a hot topic nowadays, and everybody's talking about this is not actually a new idea. Actually, it's an old idea. And both machine learning and neural networks are probably as old as, in general, digital computing. So this is a timeline of neural networks, and you see that it starts in 1943, 80 years ago. Okay, so the first ideas of neural networks started at that time. And you see that yellow curve there that looks like kind of wave, and it is to illustrate the fact that actually neural networks are had been like through different stages, where at some time they were like at the top, they were very popular. At other times they were like out of fashion. So this is interesting also to know that we have like a peak of neural networks during the 50s, then again during the 80s and 90s, and now again like 10 years ago, this wave of deep learning and all that is like the third peak of neural networks. So this, I think this is interesting to have this in context. So the idea of neural networks really starts with this paper. It's a paper from a mathematician and a neurophysiologist, McCullough and Pitts, and basically they propose the idea of what artificial neuron is. Okay, this is a very interesting work because actually at that time, in that paper, they show that neural network, which is a system made of those artificial neurons, was able to have was as powerful as any other computing device. So actually, it was equivalent to a Turing machine, which is our model of computation. We say that something which is equivalent to a Turing machine is something that has universal computation ability, and they showed that at that time. So it's very powerful. Actually, these days, everybody's talking about artificial intelligence. Probably you have heard about Wolfram, is a mathematician, the designer of Mathematica. There is a website, Wolfram Alpha, where you can use Mathematica through the web, and he was talking about all these things that are happening with ChatGPT and all that. He was talking about this, and he was saying, see, basically the concepts that we are applying right now are pretty much what these a couple of guys invented 80 years ago. There are some new things, but pretty much is basically those ideas, which I found very interesting. So there were some early works of in 1957 is the work of Rosenblatt that invented the perceptron, that was like a hardware implementation of neural networks. And then during the at the end, or during the 60s, this book was very influential. It was a very critical book of neural networks. Basically, one of the fathers, Marvin Minsky, and two of the fathers of artificial intelligence, was saying, see, the neural networks are not a way to build artificial intelligence systems. We are not going to get far trying to simulate the brain. We have to do another approach. And basically, they at that time, they almost buried neural networks. So people moved from neural networks to work to other things. And this wave is what I was telling you. So something was very important during the 80s was the invention of backpropagation, which is actually the discovery, because backpropagation was invented in some other context. But actually, what happens was that this guy Hinton uh, um, uh, discovered bad propagation as or proposed bad propagation as a mechanism to train neural networks. So this basically gave us the possibility of training more complex neural networks, more complex than the perceptron. So it was very important. And then there was like during the end of the 80s and during the 90s, really a lot of interest on neural networks. And actually, Professor Luis Fernando and myself had the opportunity to live through that interesting time of this second wave of popularity of neural networks. So actually, Professor Luis Fernando is one of the pioneers of the work on neural networks in our country. At that time, I was finishing my bachelor, and Professor Luis Fernando, who started very young. I mean, we are almost the same age. He was already a professor. He organized the first Congress on neural networks in our country with Professor Germán Hernández and Professor Luz Gloria Torres. So that was also an interesting stage. However, during that time, really this was still very academic. Some applications, some real practical application, but they were really very few. And it was more a topic like of interest in academy or and research. Okay. And again came other methods. For instance, that book is a book from Vladimir Babnik that proposed the support vector machines. And so methods with more mathematics and all that. Again, neural networks went out of fashion. And okay, I will move on. And then we are living through the third wave of popularity of neural networks. So these are some news from uh, about and nowadays there are many more news and many new things and applications of neural networks. And actually, everybody is using permanently neural networks in our cell phones, when we use our computer, when we use a search engine, when we use different services. Neural networks are everywhere nowadays. Okay, and all this is because of this deep learning boom. Okay, so okay, I will move here. And yeah, also the idea of having a large neural network, which is basically deep learning. So deep really refers to the fact that I can have a neural network that has several layers. Okay, so the depth here refers to that, to the number of layers that a neural network may have. That's an old idea. What happens is that we didn't have the algorithms and computers powerful enough to train those large neural networks. So actually, those ideas or those algorithms that start to be successful started at the like 15 years ago. Probably this is one of the okay. This is one of the old models which were we can consider like deep learning, but this is one of the first papers that use the word deep, okay, when referring to a neural network. That's from 2007, 2006, actually, also from Hinton, okay. And this started like actually the people that was working during the 80s and 90s in neural networks, some of them continue to work on that, despite the fact that many of the people working on machine learning moved to other kind of methods and algorithms. However, they just continues to work, and finally they made it work, and they were able to train large model. But the presentation in society of neural networks was really this. This event was very important. It was a challenge for recognizing objects uh, uh, in images. It is called the ImageNet Challenge. And for at that time, we are talking about 10 years ago, this was a very complex task because of the number of images that you have to use to train your model. It was 1 million. And then the number of concepts or different objects that you have to identify, those were 1,000 concepts. So the best models before deep learning have performances around 30% of error, okay, on this task. And in 2012, there was a new team that basically cut the error on half. So they got a performance around 15%, which is very, very unusual in these kind of challenges that are very popular in machine learning. Typically, the improvement from year to year is 1-2%, but these guys cut the error to half. So everybody was looking. So what was these people doing? And actually, what they were doing was doing deep learning. This is the model that's called AlexNet. It's a neural network with 8 layers and with around 60 million parameters, which was huge for that time. So that was like the presentation in society of neural networks. Okay, so was no neural network but deep learning. So what was deep learning? So I like to call it like a kind of recipe, okay? Because there are several elements. See that one element which is very important for this recipe, which is the idea of neural network. We know that from 80 years ago. So that was not enough to have the idea of artificial neuron or are combining neurons and things like that. So that was not enough. Really, deep learning is like a confluence of different factors that made it possible. Okay, so that's what I call the recipe, the deep learning recipe. Okay, so these are the elements of the recipe. So one element is the approach to do machine learning change. Typically and previously, before deep learning, this is what you see there is like the typical workflow in machine learning. You have your data, images, tests, etc. Then you have a process and actually a stage where you pre-process your data and then you extract features. It was very specialized because the kind of features that you extract for tests are different to the kind of features that you may extract from images or from graphs. So actually, people was doing machine learning on graphs long ago, probably from the 80s, 90s, probably the people were already doing in different kind of data. However, you have to do this by hand, manually, okay? Because typically a machine learning model works with uh, vectors, with numerical data. Most of the algorithms work with numerical data. So this feature extraction was very important, okay? For instance, if we are dealing with graphs, which is the topic of this course, we have to think how to extract those numbers from graphs. But you already know that there are different quantities that you can't calculate from a graph. So the average degree, the centrality, right? The clustering coefficient, etc., etc. So different quantities that you can extract from for instance, from graphs. Same thing from images, same things for tests, etc. Okay, and then you do model learning. You apply your machine learning algorithm. Then you get a model, and then typically you iterate this. You evaluate, then you improve, you evaluate, you improve, you evaluate, you improve. And when you are happy with the performance of your model, you can use it to predict over new data. Okay. So that was pre-deep learning. What happened with deep learning? This change. Basically, the one of the elements, important elements of deep learning is the realization that you can also learn the features from your data. Okay. That you can, in principle, give the raw data to your model and let your model learn to extract features. For instance, in the case of images, the input is an image, which is basically a set of pixels, right? So basically, what a neural network for image analysis, for image classification, and any other kind of tasks on images, typically convolutional neural network, basically what they do is this. They learn hierarchically different features that characterize the content of the images. So at the base, they, for instance, learn features such as edges. And then in the next layers, those edges are combined to learn or to represent object parts. And then in the superior layers, you may have concepts that are like models of whole objects and things like that. Okay, so that was a change on the perspective. Okay, these are the ideas were not new. The thing is that, as we will see, at that time we have the computational power, we have the data that made this possible. Okay, okay. So the second component, which is very important for deep learning, is the size. Okay, so deep means bigger models. Okay, this graph here is uh, uh, is showing us the evolution through the years of the models that won the competition, that competition of object classification, the ImageNet competition that we were talking about. So this here, the time years go backwards. So this is 2010, 2011, etc. This is 2015. Okay, and these are models which are predictive learning. That's the way that they call shallow models. Okay, so you see that the error was around 25, 28, and then 2012 is when AlexNet came, and the error was reduced to 16, and then and so on. You see that year after year the error was going down. So this is from the group of Alex Krichevsky and Hinton. Alex Krichevsky was the student of Hinton in the University of Toronto. This is from an university in Oxford, BGG, some model that is still used. This was Google Net from Google in 2014, and ResNet, which is still used, which is a model from Microsoft. But uh, in addition to reduce the error, see that the error, and nowadays is even below this very small error. You, here you see the increase on the size of the neural networks. Okay, so the first deep neural network were only 8 layers. Uh, the size was 8 layers, then 19 layers, then 22 layers, and in 2015, 152 layers. And this hasn't stopped. Nowadays, you maybe had been uh, uh, seeing the news and reading the news, listening to different all the different things that are happening with ChatGPT. And in the case of here, we are talking about with models with tens of millions of parameters. With large language models, we are talking about thousands on millions of parameters, billions, and almost probably the models are coming will be probably in the order of trillions. Trillions, okay, no our trillions, but the English trillions, okay, which are millions of parameters. So these are huge models, okay. Okay, so that's the other element. Uh, to train this large model, you need a lot of data. So that's the other element, that data became more and more available because of mainly, yeah, in part because of information systems, but really the main reason for having all this amount of data is internet, okay? But data alone was not enough. Okay, so something very important is the early stages of deep learning were mainly devoted to supervised learning. So you need data which is annotated. Okay, so this was also very important. The fact that there were efforts, for instance, ImageNet is an effort from a professor at that time in the Stanford University, Li Feifei, that collected a large amount of images. This was like the numbers from 5 years ago. Probably today they have much more than that. At that time, they have like almost 15 million images annotated with 20,000 concepts with bounding boxes in some cases around the objects. And all that was possible because people, real people, humans, annotated manually those images. They use crowdsourcing to do that. And nowadays that continues to be very important, that you have people, humans annotating data. So that's is not um, uh, enough to have just data. You need also to annotate data. Many of the models of these days are models that use strategies like self-supervised learning. Okay, for instance, GPT is a self-supervised model that didn't need annotation in the test. However, taking GPT, which is a language model and make ChatGPT needed annotated data. They use people from actually there was some criticism because they use people from Kenya. They pay like $2 per hour to the annotation. So they were saying that they were exploiting that people and on that. But if they pay $2 in Kenya or here, actually that's not bad. Okay, but what I want to emphasize is that having people annotating data is very important, and that's something that also enable the deep learning. So having large models and large amounts of data, you really need computational power. Okay, very important to have computational power, and that was possible because of the GPUs, graphical processing units. Okay, so the graphical processing units are a specialized hardware that initially was intended for making graphics faster in computers. Okay, however, uh, scientists realize that you can use that for doing scientific computing to do calculus which are expensive. In particular, because doing graphics like doing rendering, the rendering for doing like movies or for doing video games requires basically linear algebra to do linear algebra in a very fast way. So that's exactly what you need for many applications in the scientific computing for simulation, physical simulation, and in particular for machine learning. What you need for doing machine learning is fast linear algebra. And GPUs are really, really, really good at that. Okay. So thanks to the demand basically from gamers. There was like an scale economy that allowed those that hardware to be very cheap. Very cheap. I mean that nowadays you can buy with by 1 million, 1.5 million, a good graphic card that you can put in your computer, right? So that made like a democratization of high performance computing because actually having this kind of performance in terms of this is measured in terms of flops, teraflops. Uh, 10 or 15 years ago, it was required to have basically a supercomputer. Yes, Professor Alfonso, please go ahead.
Yes, Dr. Fabio, I have a small question. Do you hear me?
Yes, I hear you.
Okay, it's a very small question. Quantum computing has a space here. Is research in quantum computing pointing to deep learning?
Actually, that could be the next step. If we someday can have a practical quantum computers, because that will really accelerate not only machine learning, but many other kind of applications. But in particular, machine learning, definitely, we have a quantum computer. The problem is that we don't have a practical quantum computer yet. We have quantum computers and we can already use quantum computers. But the problem with those quantum computers is that one thing is that the size is not very large. They have like in the order of 100 of qubits, the last ones. And but the main problem is the noise of those computers. So there are still challenges. But if actually, I would be no surprise really if that happens soon. I'm really surprised with what is happening with artificial intelligence nowadays. So if that happens next year, I will not be surprised. But really, it's difficult to predict when we are going to have quantum computers. But that will be definitely the next stage. Lina Maria,
Yes, teacher. I have a question because uh, we are talking about the network science, machine learning, deep
right?
learning, and I want to know what is the difference or what is the branch in these topics because you, in this moment, you are talking about the hardware, but in the content, I see that we talk about the models or the algorithms or the APIs that we
Mm-hmm.
use. are the tools, and I feel that the goal is the same now from the data. Discover
That's
knowledge
right.
from the data. But when you say or you talk about machine learning, deep learning, I feel a little confused with the terms because
That's
I
right. That's right.
it's
That's
like
right. Yeah.
but
Very
depends of the models or the architecture
no.
or the hardware.
Very good question. Very good question, Lina Maria. Yes. Uh, I mean, one thing that you said, I totally agree. The goal is more or less the same, and is in general to use data and make sense of the data with different purposes. Okay. So, in the case of machine learning was the first motivation for machine learning was really as a tool to do much artificial intelligence, and that means to build systems with the ability to address complex tasks, such as being able to do pattern recognition, like doing vision, to understand language, to do planning. So the main focus of machine learning has been that. However, uh, machine learning, many of the algorithms and the approach that the machine learning use start to find use on other applications like data analytics. So during the 80s, during the 90s, people start to talk about something which nowadays that term is not used, which is data mining, minería de datos. Okay, and the purpose of data mining was basically it's basically what we call nowadays data science, to analyze and to get information and knowledge from data. And people realize that many of the algorithms that were used and developed for doing machine learning can be used to do data analytics and doing data mining at that time. So there is like a confluence of statistics and machine learning in the context of data analytics. And then the confluence of other areas, for instance, when Professor Alfonso was talking about the roots of network science, also comes from other areas of mathematics, for instance. Okay, so really what happens is that it's a confluence of different areas around of common problems. Okay, uh, I know it's difficult to navigate all this, but if I try to nowadays, what was the situation? What I would say is this: uh, machine learning is part of, definitely is part of artificial intelligence. So, okay, it continues to be part of artificial intelligence. However, one of the important applications of machine learning, okay, then you have artificial intelligence, then inside you have machine learning. Inside machine learning, you have neural networks, and inside neural networks, you have deep learning. Okay, because there are other models for machine learning which are different to neural networks. Okay, then you have oh yeah, okay. Daniel has a question, but I will try to finish answering Lina Maria. Then you have the applications, and then there is an intersection, because you have all this area that nowadays is called data science, and then in data science you have different problems of analytics that you can address with machine learning, but not only with machine learning, but also with the statistics. And then you have network science, that is also like an intersection with data analytics, data science, but also have other problems that are not necessarily inside that part. Okay, so basically what we have is like different areas of knowledge that address some similar problems in those cases, other problems which are not necessarily the same. Okay, I don't know if that made like the perspective more clear, or clearer. Sorry, Lina Maria.
Yes, teacher. Yes, thanks for
Okay,
your answer.
yeah. So and here I'm trying to tell you this story why we are nowadays experimenting what is happening with deep learning. Why deep learning has and deep learning in some way kind of how do you say eclipse the other areas, because deep learning has like an application in not only in analytics but in things like autonomous vehicles, and then in the language, and in other kind of areas, and but really those are several fields of knowledge that contribute to the same kind of problems. Okay. Okay, yeah, Daniel is asking about FGPAs, yeah, FPGAs, yeah. Those are field programmable gated arrays, which are some kind of specialized circuits. Yes, there are some areas where those has been used, but what I see nowadays is that basically what is dominating is GPUs. So some people was proposing that, but I think that's very niche. And most of the work nowadays is done is with this kind of hardware. Okay, okay, I will continue. Something very important about this that has to do with what you were studying these days, that I request you to study, is that programming this kind of hardware is difficult. Okay, so actually, when they started to realize that you can use GPUs to other applications, they developed some frameworks. NVIDIA, which is the leading company on this area, they developed something which is called CUDA, but that was very difficult to program. It was C, basically C, and it was very low level. So something that was very important also for this sources of deep learning was the development of platforms, so and the programming libraries, and programming frameworks that allow to use this kind of hardware in an easy way. I mean, without really having to understand the details of how the parallelisms work, and all that. So all this abstraction that is provided by frameworks like TensorFlow and all Torch, PyTorch, etc., is very important for this popularization of deep learning. So this is also very important, and that's why using these tools nowadays, and working on this, is very important to know at least one of these frameworks. Okay, TensorFlow is one of the popular ones, and PyTorch is also becoming in fact, is more popular in research nowadays than TensorFlow. Okay, okay, and that's something that we are going to discuss later. Okay. Okay, these are some examples of the code using CUDA, Theano, this and all model. What these kind of frameworks do inside is basically build computational graphs and optimize those computational graphs, and those computational graphs allow to easily map to the hardware, to CPU, GPU, multiple GPUs, multiple computers, but all that really is abstracted away, and as a user, you don't have to worry about that. Okay, so this is Keras, so which is the one that you were reviewing, and is very expressive, very easy to use. Okay, so that was another element. Other important are algorithms. So there are some classic algorithms. Most of the algorithms that are used nowadays were invented during the 80s and the 90s. There are some new algorithms, some new approaches, and many tricks. This is very engineering. Okay, so machine learning is like a kind of pendulum. Okay, so at some times is in an extreme where the focus is more on the theory, the math, the statistics. Okay, and at other time, like right now, the focus is in the engineering part. So doing deep learning is very engineering, in the sense that is a trial and error. Actually, for instance, this book, the neural networks tricks of the trade, like the literal or the translation will be something like the los trucos del negocio. Okay, you will think that is like a uh, any book, and actually no, it's a edited book with different chapters, and all the big names in machine learning wrote a chapter in that book. Okay, so those are like the really the serious people working on neural networks, and they wrote a book about the tricks because this is full of tricks. Okay, and what are the tricks? All these are tricks, different mechanisms, different activation functions, things that made training the neural networks easier. So nowadays, if you want to build a deep learning model, you have to be aware of those tricks and you have to know those tricks. So that's actually something that I don't like that much, but no way, you have to use that and deal with that. Okay. Okay. So yeah, several applications, etc., etc., etc. Okay. So something that I asked you to review was and let me here open quickly the notebook that asked you to review. So actually, let me share with you this. Hmm, actually, I think I will do this. Right. So let me share with you this window. Yeah, this one. So I asked you to review. Wow, 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 wow. Let me see. So this is our class. Okay. So I asked you to review this. Yeah. So did you have time to take a look to this, guys?
Yes.
Okay,
Yes.
good, good. So I will quickly over this and then answer some questions if you have some questions. But I will ask you to make this more interactive about some of the things that we are doing here. So anybody that want to, we will quickly over this, but I think we can make it more. Interesting if you help me guys to quickly go over this notebook. So anybody that wants to tell us what we are going doing, what we are doing here, please raise your hand. Okay, let me. Oh, sorry. Okay, Jonathan, please. Jonathan, you can open your mic.
Okay, I think the other
Yeah.
Jonathan in this in
Oh,
this.
Jonathan Javier. Right.
Oh, okay, thank you. In this, you are defining like the model with the neural network model with
Okay.
this is one of the type that you use to define this model.
Uh
So
huh.
you use the sequential when you
Right.
define that the model is yes, it's a sequential. So you use dense at the layer
Mhm.
where it,
Oh,
this dense connect the previous layer with the actual
which is
layer,
the
and
which okay. But one thing, Jonathan, quickly. So yeah, as Jonathan said, this is one of the ways of defining a model in Keras. There are different ways to do it, but I think this is one of the simpler. And it is called sequential because you put the layers. Your neural network is made of layers, and you put the layers one after the other, right? So the first one here, as Jonathan was saying, is a dense layer, and this is connected to what,
this is connected
Jonathan?
to inputs
To
or
the input,
to,
right? To the input, right? So and the
or
input is, yeah, is two values. Is what we are telling
yes,
it there. Yeah. Okay. 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 And then this layer has 20 units.
yes,
Okay. 20 neurons. Okay. And then this one.
In this, you define the activation function that in this case is a RELU, a
Mhm.
RELU function
Okay.
that is applied
Okay.
to the previous to calculate the weights to the previous neurons.
Mm-hmm.
And then you is defined the other layer that in this case is a one neuron,
Mm-hmm.
and the activation of this neuron is a sigmoid function.
Right, exactly. So it's a very simple neural network. Here is like the summary of that neural network. Okay. Here is telling me what are the parameters of the model. Thank you, Jonathan. Anybody can tell me why we have here 60 parameters? Anybody? And here we have 0 parameters.
The
And here,
weights, they are the weights of the each
right.
neuron connecting with the
Right.
data and the output neuron.
Okay. So why 60? Why exactly 60? How is the
Because
how
there
can we calculate that 60?
we have two inputs.
We have
And
two inputs, right?
for every in the first ledger, where we
Right.
have 40
Yeah.
40
Right. So two
parameters,
right. So two neurons connected to 20 neurons. So the possible combinations are 40. So we had 40 weights. And then
and one output and 20 neuron, or the bias.
the bias. So in addition to the yeah, because to calculate the activation of a neuron, you multiply by the inputs by the weights, and then you add an independent term, which is called the bias. Yeah, Ricardo probably was saying that. Yeah, Ricardo, thank you. So is 2 times 20, 40 plus 20, because you have a bias for each neuron, is 60, okay? And same thing here, okay? Why don't we have parameters for the activation?
Because it's a function.
It's just applying a function that doesn't have parameters. So this doesn't have parameters. So in total, our neural network has 81 parameters, okay? And all of them are trainable. There are cases where we can say we don't want to train this, we want to train this. So this number, the total number of parameters, may be different to trainable parameters, but yeah. So that's a very simple. Okay. So anybody else that okay, and this is like a graphical depiction of what's going on, right? This probably is clearer. So this is the input is two neurons, or better, two values, because these are not neurons. And then those two values are connected to 20 neurons. And then those 20 neurons are connected to other 20 neurons. Really, this is not, this is a function that is applied to each neuron independently. And then you connect those 20 to one output neuron, which also have an activation function. Okay. Okay. Somebody else that wants to continue explaining what we have here? Yeah, I saw some hands raised before Jonathan explained. So anybody else? Yeah, please go ahead. I don't see who is opening the mic. Yeah, please go ahead, guys.
Maybe teacher, the last
Juan
layer.
Sebastian, right?
Yes, the last layer is have output of one.
Mm-hmm.
This means with the other layer have sigmoid function. Maybe
Mm-hmm.
this have a value between 0 and 1.
Right, that's right. Yeah, that we specified that
Classification,
there. Right, right.
yes.
Because
Classification model,
right.
yes.
Yeah, because we want to do classification, so the output is a value between 0 and 1. Okay, and then what are we doing here in this code?
Um, we are defining the optimizer because we
Right.
need to perform gradient descent or
Mhm.
well to
Right.
update the weights and to
So
train the
something,
model.
yeah, something which is very important for in general machine learning, by particular neural networks, is that you learn by optimizing. And basically, optimizing here means to minimize a loss function. Okay, so here we are telling that the optimizer that we are going to use is something which is called SGD, which is stochastic gradient descent. Okay, it has some parameters. And then we are minimizing something which is called the binary cross entropy. Edwin knows what the binary cross entropy is.
Yeah, it's log loss. Actually, this is for two classes, I think, binary cross
Mm-hmm.
entropy.
Uh-huh.
And well, it's basically
Yeah, let's
if
look
my
for the question.
prediction and the class, the true class, are exactly the same, well, the loss will be zero.
Right,
Otherwise, it will be the
right.
maximum,
So
right?
yeah, this is basically the formula. Okay, is the yeah where oh okay sorry this is the let me see what is the formula. Yeah, this is but this is not. Let's look at something which is for two classes. This is a gentle introduction. So let's see how gentle it is. I want the question. What is the question?
Maybe in Google Images.
Yeah, better in images. You're right. Yeah. Oh, here. Yeah, there it is. Yeah, yeah. That's no. This is yeah.
I
Let's
guess
look at
it
the
was the
images.
entropy. I guess it is
Yeah.
just the entropy for one class.
Yeah, that's for one class. Let's see. Yeah, for instance, this one. This I think this is okay.
Yeah, but
Yeah.
the only difference is that you have the two classes, so you have to point to the
Mhm.
difference between the logarithms.
Right. So here, yeah, this is the expression exactly for two classes, okay? Where you have like a binary. So here, anybody can explain this, what binary cross entropy, how binary cross entropy works? This expression that we have here at the bottom. What's the idea?
Well, I guess the general idea of the cross entropy is kind of measuring the amount of data you're I mean the amount of information you are using and how the difference is minimized
Right.
between
Right. So you are comparing two things. You are comparing the real labels of your data
yeah
versus the prediction of your model. So in this expression, where is the prediction of your model?
the first part. The prediction.
The prediction
Yeah,
of your model.
the first one.
Yeah, the prediction is this, right?
If yes,
This
yeah,
part. This part is the
exactly.
prediction. F of x1, okay?
Uh-huh.
Yeah, F of S1. F of S1 is the prediction. And then the real label is this one,
The
right?
T.
The
Yes,
T, right?
yeah,
T.
right.
So this expression is see that you consider the two cases, okay, where you consider T1 multiplied by the logarithm of the prediction and then 1 minus T1 with the logarithm of 1 minus times the logarithm of 1 minus minus the prediction, okay? So it helps to understand what Yoda was saying is right. Really, the motivation is from information theory. But we want to see what's going on. You can see what happens, for instance, when your prediction is equal to the label. So it's in two cases where both are 1 and 1, or when both are 0 and 0. When both are 1 and 1, you have here 1, and then logarithm of 1 is 0, so this is 0. And same thing here. 1 minus 1 is 0, so multiplied by this is 0. So when both prediction and the real label are the same, this is going to be 0, okay? But when they are different, then here you get, for instance, this is 1, and then, for instance, if this is 1 and this is 0, actually here what you are going to have is the logarithm of 0 is minus infinite. So really what happens is that you are going to have in a computer, really you are not going to get minus infinite, but you are going
A
to
huge
get,
number.
yeah, you will get something which is a very negative number, right?
Yeah,
Uh,
huge negative number.
a huge negative number. I hear the same thing, okay? So what happens is that and see that this is minus minus. So really what happens is that when the prediction and the real label are different, you are going to get a large number. When they are the same, you are going to, or almost the same or very close, you are going to get a small value, which is what you expect from a loss function, okay? Okay, good. So let's go back to the, where is it? Here. Where is the notebook? Oh, here it is. Okay, okay. So yeah, here we are telling two things, the optimizer and then the loss function that we want to optimize. And then here we fit the model and then we can see how it works. Okay, and it does uh, not that bad work trying to separate these two classes, okay? Okay, here we have an example for a test classifier. So this is just an example, something that I was telling that depending on the data, you have to extract information in some particular way. Here you have to do something which is called tokenization, etc. So there is some particular processing that you have to do to your data. And here we are training again a very simple model, but with more, see that now the input layer is of 1000, okay? Because the representation of our test is based on the appearance of some words, and we have a vocabulary of 1000, so it's much bigger. And then we have a dense layer of 256 neurons. So yeah, we have here around 250, 260,000 parameters. It's a bigger model, but the idea is basically the same, okay? So any question about Keras? Did you have the opportunity to play with this? Any question? Everything clear about this? Jonathan,
Yeah, actually, it is not about Keras per se, but
sure.
I was wondering about this text classification.
Hmm.
Uh, the first part is finding the embedding. I mean the tokenization of the
Right,
data.
but really, really here what happens is that we are using a very simple representation of our test. Actually, this kind of a representation is a representation based. So typically, this was like the classical way of doing it. That is
Yeah, sure, sure.
using so no, we are not using an embedding. Really what we are doing here is having a large binary vector that tells you if a word is present or not in the test. That's all what we are doing, okay? So another alternative is to use an embedding. What's that thing of the embedding? See, here for instance, let me see. This is for instance for the what's that? Yeah, this is like a vector representing a test. Basically, the ones here represent the fact that there is a word. There is a list of words. So the first word is not present, the second is present, the third is present, and so on. So basically, this is a very crude representation of a test. Okay, what's the problem with this kind of representation? That in your vocabulary, maybe there are two words which are very close in meaning. For instance, you may have the verb run here, and then here running, and here you have runner. All of them are related, but here they are separate. They are not related in any way. So something which is more flexible is to represent each word not just with a binary value, but with a vector. That's what is called an embedding. Okay. So actually, we are going to use sort of no, no, really, we are not going to use really embeddings, but that's a way to represent tests that is more elaborated. Okay, but this is a very simple way to represent tests. I don't know if that answers your question,
Yeah,
Jonathan.
yeah, sure. But I was wondering. I mean, this embedding could be as simpler as simple as you can show here, or for example, as difficult as complex as transformer, for example. But but I was wondering if maybe preliminary step. I mean, something that provide like a dimensionally reduction before the the deep learning. I mean, it could improve the results. I mean, in this case of NLPT or text recognition, it shows that there is that it is a necessity, but I don't know if maybe adding some pre-processing steps that reduce dimensionality could improve the all. Or my question is if it always improve the results.
Okay, so just to clarify, Jonathan, then I will answer your question. So an embedding is this: it represent a word as a vector of numbers. Okay, it doesn't mean here in this particular example they put like an interpretation to each field of the vector, but actually this is not what we do. Really, the what happens with the embeddings are that the embeddings are automatically learned. Okay, so words are represented as and Ricardo was asking what an embedding was. So an embedding is to represent a word as a vector in some high dimension. Actually, no very high dimensional. Typically, the embeddings are of some hundreds. For instance, for a typical transformer like BERT, is 700. It's a vector of 700
Yeah,
position.
yeah,
Okay.
but here in text, I mean, the embedding is a necessity because you have words and you have a representation of the words. It is
Yes,
a necessity.
but Jonathan, uh, there are different ways to represent. So
Yeah, sure, sure.
actually, you can think of the thing is that really you don't call that an embedding, but when you count the frequencies of your words, you can think like the vector representing a word is like a one hot is a vector with one and a zero in the rest of the positions.
Yeah, yeah,
Okay.
yeah. Like like a frequency. Yeah,
Yeah, but you don't call really that an embedding. Really, when you talk about embeddings, you are talking about something like this. Okay.
yeah, yeah, yeah. Sure.
Yeah.
Yes.
And
Something that
then
is relevant.
yeah, and then typically you don't apply dimensionality reduction to this. You can apply dimensionality reduction to the represent. Yeah, because one thing is represent the words and another thing is represent the documents. Yeah, when you are representing documents, you can't apply dimensionality reduction. Yeah, definitely. However, what happens in the modern models is that that reduction is in some way implicit in your model. Okay. For instance, in transformers, it's not explicit, but it's implicit
Yeah,
there.
yeah. But for example, in images, it sounds redundant. I mean, we all know that deep neural networks used to reduce the dimensionality of the image inside of the network.
Not necessarily. It depends on what kind of model you are
Well,
using.
yeah, yeah. For example, in autoencoders or something like that.
Yeah, for instance, in models that yeah, you can impose different kind of restrictions for force your model to learn. Okay, so one restriction is definitely the dimensionality, but not necessarily. Okay, no necessarily is the yeah, but for instance in convolutional neural network there is some reduction on the dimensionality, but actually it's not that much.
Yeah, yeah, yeah.
Yeah, actually the vector that you get from a network for image recognition usually are 2000 or 4000 in some cases, things like that. Okay, so but the important thing is that in all these examples is that in neural networks and deep neural networks, really you learn the representation of your data. For instance, in the case of tests, your model learn to represent and to know that a cat and a kitten are things which are related, and the representation that is learned is going to be very, very close, as is shown here. And things like dog is going to be a little bit farther, and then houses, which is not an animal, is going to be even farther. Okay, so but that's automatically learned by the model. Okay, okay. Any other question or comment? Yeah, in fact, with embeddings, I can compare okay, yeah, in the view that it was mentioned as similar to the one used in the base. Yeah, that's also important how to compare the object that you learn. So typically cosine similarity, for instance, in this kind of representation. Lina.
Sure, I'm not expert on the topic, but I want to ask you. I will review the content and some things about TensorFlow and Keras, and I feel that Keras is an app or a tool to make very easy the analytics process, that like things that you are talking with Jonathan in this moment. I feel that in this is not necessary be an expert in the concept of like the
Right.
expert in terms about the network, because with the some lines are used tools with Keras is so it's very easy, for
That's
example,
right.
that case. But my point is necessary to review the literature about the gradient, or there that things that are properties for the network sign, the network, or only just know the concept and
No,
the tools or the functions that I can use with Keras or TensorFlow.
no, that's a good question, Lina. That's right. That's right. The frameworks and the tools that we have available nowadays made developing some kind of models is really, really easier than it used to be like 10 years ago. Okay, so the question is if you really need to go deeper and to study all those concepts and all that math that is behind these models. It depends on what you want. Okay, for instance, let me give you an example. 20 years ago, if you wanted to have like a website for a business, okay, you really need to be an engineer to build that website and be able to have like a store, and then to the people able to navigate the inventory, and then they wanted to buy something, choose what they wanted, and then paid and all that. You need to be an engineer to build a website. Nowadays, what happens if you want to build a website to sell whatever you want? You really don't need to be an engineer. You can use Wix, okay, and you can create your website that is going to look really, really, really well. You can put there are many components, it's very graphical, and you don't have to care about the details. However, if nowadays you want to really do a web application, a complex web application, you really need to be an engineer to do that. Okay, so it depends on the complexity of the task that you want to solve. Okay, so there are many things that nowadays is easy to do. For instance, do object recognition for natural objects or things like that. You can use services from Google, from Microsoft, from Amazon, that help you to do that in a very easy way without worrying about the details. However, if you want to build something which is more specialized, right? For instance, you don't want to recognize cats and dogs, but you want to recognize it in a medical image there is a tumor or not. Yeah, you cannot use those services, and you really need to understand better this kind of model. So it depends on the complexity of what you want to do, right? I don't know if that answered your question, Lina.
Yes, yes, teacher, thank you.
Yes, so nowadays it's easier. What's the problem with that? That nowadays, if you want to make a living out of doing web pages, it's difficult. That's very, very. I mean, there is a lot of competition, but because many people is able to do simple web pages. Okay, so it's difficult to make a living out of that. Same thing in this. If you want to build simple machine learning models, nowadays really that's not something that it's something that many people is able to do, right? But if you want to build things which are complex, yeah, that's you need a lot of more knowledge on that topic. You need to go deeper, and the good thing of that is that not many people is able to do that. So that's an advantage. Jonathan.
Just something to add, and is about the problem, because you can try for, I mean, I guess for all the problems you can find, you can test with previously, I mean, a pre-designed tool. But the
That's
thing
right.
is that if it doesn't work, you don't know why.
That's good point from Jonathan. That's an example that I like to to give. You can think of this kind of machine learning models and algorithms like a bots with several buttons, switches, dials, lights. Okay, and usually that works well with some problems, and you put data, and at the other side you get a classification model. But what happens if it doesn't work? So you had many dials there, and you had many button switches, so and lights, and you say, okay, what can I do? Let's see what happens if I press this button. Nothing. And let's move this dial. Nothing. Yeah, because if you look at this as a black box, it's very difficult to know exactly what you have to move to make it work. Okay, so yeah, thank you, Jonathan. Yeah, I think that's a good word. So the thing is, when this doesn't work, you really need to understand better what's going on. Okay, 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 good, great. So let's move to the next part before going to
Professor,
the
I
break.
don't know if this is sorry for disturbing you. If this is the right time to have our break, our usual break.
No, but I will. Let's do the following. I want to start with the second part. To go quickly over that, and then we can go to the break around 7:40,
Okay, let's move
right?
on.
And
Thank you.
then yeah, but yeah, 7:40. Let's try to do probably before that. But
Okay.
okay, so this here is a document. I'm sharing my screen. Yes, right? No. Yes, I'm sharing my screen. So
Yes, you are.
thank you. Okay, the link to this document is in the material of the class. Okay, so actually, this is an interesting experiment. It was a kind of journal that had like kind of interactive papers. I didn't know about this. And actually, this was like an experiment that lasts like for 5 years or something like that. But it didn't continue. That's bad, but because yeah, I realized that this has a lot of work. However, some people, this document in particular, actually, I will use it as a kind of presentation because it's interactive. Was done by some people from Google Research, and it has a lot of work and is very good. So I really recommend you to take a look. I will go over it with, I mean, no in depth, but I will choose and explain some things. But I suggest you to read it because it's very easy and very didactical. Can you say that? And yeah, it is very good. Okay. So, what's a graph neural network? So, the idea of a graph neural network is basically to have a neural network that is able to exploit the characteristics of graphs, which are very particular, okay? Which are very particular, okay? So, what are we interested in a graph? That's something that you have already studied during the course. But from the point of view of machine learning, really you have information at different levels. Okay, then you have information at the global level. Okay, for instance, so those are some kind of attributes that you may get from a graph: the number of nodes, the longest path, okay, the diameter, etc., etc., etc. And actually, you have studied many of those. Okay. In addition, you may have information on the nodes. Okay. So, which here are called the vertex. Okay. For instance, if this is a network or a citation network, where the nodes are papers and the edges are indicates that one paper cites another one. This could be information about, in each node you may have information about this paper. Actually, some representation of the text on the paper, okay? So those will be the vertex attributes. If this is a social network, this could be information about the profile of each of the user of the social network. Okay, and then you may have also information on the edges. Okay, the edges. Also, you may have attributes. For instance, if this is a social network, you here may codify the information about the interaction between these two subjects, right? So information about how many messages they interchange, the content of those messages, etc., etc., etc. Okay. So actually, here we were talking about embeddings. So actually, for a graph, we may have some kind of representation that for vertex, for vertices, for edges, and also a global representation. Okay, so the challenge of dealing with graphs when we try to apply neural networks is how to use that information that is structured in a very particular way. Okay, and it's not very homogeneous. Some analogy that they do here is, for instance, images. Images also have a structure, right? However, the structure in an image is more homogeneous, right? Because images are arranged as matrices, and all the images independently, those are natural images or images of from a satellite or images, a medical image, all of them are arranged in the same way, more or less. Okay, so that's an advantage. But a graph is something which is really very heterogeneous, and that's really a challenge. Okay, okay. So yeah, you already know this, where to find graphs. So you may have graphs in different contexts. I was talking about the images, which are typically a typical kind of data that is processed by deep neural networks. And then actually you can think of an image as a graph. I don't know if this has been discussed already in the course, but yeah, you can think of an image as the pixels and their relationship. So for a particular pixel, there is a neighborhood relationship with the neighbor pixels, right? So you can look in an image as a graph. And actually, this analogy is interesting because the motivation of some of the graph neural networks is to take ideas from neural networks, for instance, convolutional neural networks, which are adapted to images, and try to generalize those ideas to working graphs. Okay, so but again, one advantage of dealing, for instance, with images is that they are very homogeneous. Okay, you can see that in the how do you pronounce that? Adjacency
Adjacent.
adjacency matrix,
Adjacency matrix. Yeah.
right? Okay, adjacency matrix is very homogeneous, okay? And that's an advantage that's exploited by a neural network. If you want to take those ideas from neural network from images and extend it to graphs, there are some challenges that you have to solve, okay? Also, you can think of tests as graphs, okay? Because the sequence of the words in the test are in some way a relationship. So also you can look at that and see that this actually this document is written like a motivation from people from machine learning. So they are trying to introduce the notion of graphs to people that work with machine learning. Okay. Now this is the kind of graph that you are already used to. For instance, molecules. Okay, or this is more complex graphs. This is a social graph. These are the interactions of the actors or the characters in a play. Okay, so yeah, and there is a challenge. See, if you are thinking, okay, I'll try to use ideas from the neural networks on the kind of data that I work on to apply to graphs. So something that results very natural is to say, okay, the adjacency matrix is like a natural representation of a graph, is numeric, is a matrix. I can feed that to a neural network and see what happens. Okay. What's the problem? Because actually you can think, see, this in some way similar to an image, right? Where you have the pixels, and then yeah, I can fit directly the adjacency matrix to my neural network. The problem with this, oh, okay, this is the another network that you know very well, the karate network. The problem with this is that what happens is, let me, I will uh, 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 skip, I will go back to show what the problem is. The problem is that the adjacency matrix, when you depends on the order of the nodes or the vertices. Okay, so see, this is exactly the same graph. This is the adjacency matrix for the same graph, but what happens here is that the nodes are sorted in a different way. Okay, yeah, there is not a natural order. Right? Thank you, Ricardo. Exactly, that's what happens. What's the natural order of a graph? There is no natural order. See that in an image, there is a natural order because of the position of the pixels, okay? But in a graph in general, there is a natural order. And see what happens. This is a graph with only 4 nodes, okay? Only 4 nodes. And all these are adjacency matrices of the same graphs. What changes is like the order of the nodes. And then when I move, see, here we have actually 1, 2, 3, 8 by 3, 24 different adjacency metrics to represent the same graph. So that's a problem. So like a naive representation of the graph to feed it to a neural network as an is adjacency matrix is something that really will not work. Okay, so that's a problem. Okay, so that's a challenge, and we will see how it is addressed. Okay. Uh, what kind of problems we may have from the point of view on machine learning, the typical problems on machine learning? Okay, so we may have, for instance, a problem where each instance or each sample that we want to process is a graph. For instance, this could be molecules, and then I want to classify the molecules according to one property, okay? So this is a task at the level of a graph, okay? So each instance is a graph, and then what I want to do is to predict a label, for instance, for each graph. So each graph is independent of the other graphs, and this is very similar to what we typically doing machine learning problems. Then we have problems at the at the level of the node. Okay, so here our problem is I am given a graph, only one graph, and then my instances are the nodes. Okay, the instances are the nodes. For instance, this could be a social network, and then this could be a classification of the nodes of the social network according to. For instance, I want to predict if some of the members of the social network are more willing to buy some product, a cell phone, or less willing to buy a cell phone if I'm using this for marketing. Okay, so the input, my training data set, and I mean, my data set is a graph. And then I have to do, for instance, predictions at the level of the node. Okay. So this is a node level task. Okay. And then we may have edge level task. Here, the example is I have for instance, objects or actors or elements in a scene, and I want to predict what's the relationship between those actors or those objects in the scene. Okay, so really, what I have to, my model has to be able to predict is something which is at the level of the edges. Okay, so this is called an edge label task. Okay, so just thinking from the point of view of somebody that wants to develop a framework for doing learning with graphs, you start to think, wow, that's difficult. How do you represent the data? How do you deal with in the same framework with the same kind of with all these possibilities that you may have? And actually, that's something which is interesting about the frameworks. Today, we are going to discuss about one framework which is called Spectral. We are going to use it, and we will see how they deal with that challenge. Okay. Okay. I think this is good time to stop for a break. Professor Luis Fernando, how long is the break? 15 minutes? Or
15
15
minutes.
minutes. Okay, great. So it's 7:35, so we'll meet again at 7:50, right?
Yes.
Okay. So
See you then.
okay, but while you are doing whatever you are, you are going to have dinner, something like that. If you have time to take a look to this document, that will be nice. And if you have the opportunity to go to the document and go to this part, okay, which is interactive, and this is the link of the document is in classroom, and please play with this. And when we come back, we are going to discuss about this. Okay. Yeah, thank you, Daniel, for the link. Thank you very much. Okay, so see you in at 7:50. Thank you.
Okay, thank you.
Okay, we are back. Okay, so everybody back. Great. Okay, so as I was saying, it's not clear how to represent the information for feeding a neural network. The information of a graph to feed in a neural network, which is true, is that definitely we have information at the level of nodes, at the level of edges, and typically that's the kind of the information that we want to model. But eventually we may have additional information, for instance, information at the level of the graph. And the question is how to uh, deal with that information to feed to the network, and how to do learning. Okay, so we will see different alternatives. Okay, so here, this is like the kind of the simplest model that we may have. So what's this? So we have a graph, right? And then we have information at the level of the whole graph, at the level of the vertices or nodes, and at the level of the edges. Okay, and then here what we call F is basically a neural network. It is shown here, but see that we process independently the information of the global information, the information of the vertices, and the information of the edges. Okay, so really what happens is that we keep the structure of the graph, but eventually what we change is the information that is associated to the whole graph, to each node, and to each edge. Okay, and then we can train a neural network to do that. And this, what we are depicting here, is what will be like a kind of ledger. Okay, so think of this as a generalization of what we have in a conventional neural network. For instance, in Keras, we have dense um, layers. Okay, so a dense layer, basically what it does is it maps a vector to a vector. So here, instead of having only one vector, what we have is a whole graph that have information at the global level. So different one vector for the whole graph, a set of vectors for each one of the vertices, and a set of vectors for each one of the edges. And then the layer will map all of those vectors to new vectors that will be associated with the whole graph, the nodes, and the vertices. Okay, okay. So that's like the simplest model that we can think of, where we don't have interaction between the edges and the vertices, or the vertices and the whole graph. Okay, okay. For instance, something that if our task is a task at the node level, basically what happens is that, for instance, this will be a model that takes the information of the vertex and process the information of each vertex, of each node, and made a prediction that will be like assigning a class to each one of the nodes. Actually, here we are not exploiting the structure of the graph. And in the third part of today's session, we are going exactly to do that. Our baseline model is going to do exactly this. Okay. So in principle, this is a graph neural network, but it's a neural network that is ignoring the structure of the graph. Okay. Okay. Then uh, one possibility that we have to integrate information is to uh, for instance, what we are doing here. So here we have information about the in the edges, but we don't have information in the nodes. Okay. So how do we integrate the information from the edges to get information in the nodes? Remember, and actually it was good idea. Thanks, Jonathan, that brought the topic of the embeddings, because actually what we are doing here is assigning vectors to different parts of the graphs. In this particular example that we are looking at here, we are assigning embeddings, vectors, to each one of the edges. So we have information about the edges. And then what we are doing is, for instance, here for each one of these nodes, for instance, let's choose this node that has two edges. So what we do is we integrate the information of the edges, which are associated with this node, to get information for this particular node. Okay, this kind of operation is called pooling. Okay, because it's an aggregation of information. So we can use the information of the edges to build information for the nodes. Okay, so graphically we can depict this in this way. Okay, so remember, here was a very simple model which we have information at the level of nodes, and then we use that information at the level of nodes, so the vertices, and we apply the function, for instance, a classifier for classifying the nodes. Here, yes, Ricardo.
Uh, I'm sorry. It seems a little bit strange for me because the how we know we are summing the all the vectors, but how we know that we are not zooming things that I mean it has to be in the same scale because
That's
if not
right.
we
That's
are
right. That's right. That's right.
adding.
Yeah, let me give you an example. Suppose that this is a social network. Okay. Typically, in general, I can have information, and these are each one is node here is a person in that social network. Okay, and typically I can have information of each actor, of each person in the social network, right? However, because of privacy, I don't want to store information about the people, okay, of the individuals. I only store the information about their interactions. Okay. For instance, it could be a vector representing the most frequent words of the messages that two person interchange. Okay, so for instance, the representation of this edge here is a vector with the frequencies of the words that the people use in their messages. Okay, so yeah, to do exactly what you said, how can I integrate that information? The information of this edge in some way has to be compatible with the information of this age and information of this age and this age. They are representing the same. They must have the same dimension. Okay. So when I add them, it makes sense to add them. Okay.
Yes, but for example, we have here four arrows,
Mhm.
and it's summing five
Oh, yeah. What was the
vectors.
fifth one?
The fifth one is the node, but that I guess I don't know.
No, you know what? I don't know. I don't know, but actually, they put this graph to motivate this one. Yeah, I will not put, I will put only the information of the, yeah, you can have the information of the nodes, right? However, really what I want to illustrate here, and I think is what they want to illustrate, so that I don't know why they have five and not four. Yeah, and yeah, you're right, they had one more that could be on the node. But here for this graph, actually what is happening is that you are not using any information of the nodes. You are only using information of the edges. Okay. I
That
will
makes
say,
sense.
yeah, I will say that this is a mistake, but probably I'm overlooking something. But from my understanding, and the motivation, yeah, because they said yeah, here they say we are gathering information from the edges to the nodes. This goes from the edges to the nodes. So yeah, I think they shouldn't have here three but two, for instance, for Nino, and for this one two, and for this one four. Okay. Okay,
Okay.
so this is just to illustrate a particular case where, in fact, I can gather information from the edges to the nodes. Okay, and the other, and the opposite thing, I can also gather information from the nodes to the edges. Okay, see that all this is about representation of information. Okay, with the purpose of transforming that information. By the way, what I'm showing here is, yeah, these are like the final layer, and these are node predictions, but in general this could happen in any intermediate layer of the neural network, and sometimes these representations are really learned by the neural network. Okay. Okay, so I can gather information from the edges to the nodes. I can gather information from the nodes to the edges. Okay, and I can gather information from the vertices to the or from the nodes to the whole graph. Okay, if I'm going to, for instance, global prediction. Okay, and then I can combine this. Okay, so typically in a graph neural network, basically what you have is something like this. You have an input graph, and then you have different layers that transform the information that you have at the level of nodes, edges, and at the level of the graph. Okay. Okay. Uh, there is some concept that is used as a way of abstracting what's going on when you are dealing with the information in the graph in a neural network, that is mesas passing. Okay. So what was the idea? The idea is that actually you can, for instance, integrate information from nodes that are connected to other nodes. So here, let's see if, in fact, here now this is right, but here the concept that they are illustrating is different. So, for instance, let's see this node. This node has its own information, but it integrates information from the other nodes, from the neighboring nodes. In this case, for this node here, the neighboring nodes are this and this. Okay, so it integrates its own information plus the information of the neighboring nodes, and same for the others. Okay, so this is called mesas passing, and this is typical. And in fact, the example that we are going to look at later, which is one of the first graph neural network models, is what it does. Okay, so in one layer, this is the layer N, we integrate that information, we apply that transformation, which is basically a neural network, some layers of a neural network. Typically is a linear transformation plus some non-linearity. And then at layer n plus one, yeah, we get that integrated information. So for instance, here, this is the node. It integrates information from the neighboring nodes, and this is the integrated representation. You apply the function, and then you get a transformed representation, and this is the new representation for that node. Okay, and for all the nodes, it's exactly the same. Okay, for all the nodes, it's exactly the same process. Okay, so actually, what this does is a kind of generalization of what, for instance, convolutional neural networks do with images. Okay, but this is more general. Okay, because uh, every image can be seen as a graph, but not every graph can be seen as an image. Okay? Okay. So this operation that we are doing here can be seen like this. It's like you use the information of the nodes and the neighboring nodes. So this is like a transform from nodes to nodes, and then you apply some function, and then you get new the same graph but with new information. Okay, and then you can do different combination of all these. Then, for instance, here you can send information from integrate information from the vertices to the edges, and from the edges to the back to the vertices. And then you can interchange that, for instance, from vertices. This goes from edges to vertices, vertices to edges, and then in parallel you do the same from the opposite, from edges to vertices, and from vertices to edges, and to edges to vertices, and then you can combine all that. So see that the possibilities are multiple. So different graph neural networks use different combination of these strategies. So this is a kind of general framework, okay? And then you can add the global representation and things like that. So the important thing here in a graph neural network is how it integrates all this information, okay? Okay, this is an example of a model. This is a task at the level of the graph. Okay, so this is something like this, like the first one example that we saw here. So each instance is a graph, okay, and then we want to classify, for instance, in two classes. So this is a real problem where we had molecules, and we want to classify those molecules according to some chemical property, okay? The chemical property is this one. Yeah, you want to classify according to the odor. Actually, there is an odor data set, and it has some labels that are associated with the per sets. And in particular, in this example, they want to classify the smell of the molecule as pungent or non-pungent. Pungent is a strong, striking smell. For example, the smell of garlic and mustard. Okay. Okay, and that's what they want to do, classify between pungent and non-pungent. Okay. So here, every point here, if you click a point here, you will see the molecule at the right. Okay. So this is the molecule at the right. And then this is the output of the model. So the inside, the color inside each circle here is the real label of the, sorry, no, is the prediction of the model. And the circle around, the color of the circle around is the classification, okay? So for instance, this one is a sample that is well classified by the model because it's pungent, and the model prediction is pungent. And this is an example of a bad classified sample. Okay, the sample is pungent, but the classification of the model is only 2% pungent, is non-pungent. Okay, so what you can play with here is with different configuration of the network with different aggregation functions. To aggregate, this aggregation function is how you, for instance, aggregate the information of edges to vector, from vectors to vector, or from sorry, edges to nodes, nodes to edges, or nodes to nodes. Okay, and then you see if you have information at the level of node, at the level of edge, or at the level of at the global level, and then the size of the embedding, how large is the representation for each one, and this is showing you the different models. Okay, AUC is the area under the rod curve, which is a measure of how good the model is doing it. You can see that different combination produce a different performance of the model. The bigger the better. The optimal value will be 1. Okay, and here they have a graph comparing different configurations. And then here is the test AUC, okay? And this is the number of parameters of your model. So see that not necessarily to having more parameters is better, okay? So actually this one is a good, is the best performing model, and you can see the different parameters, and it's not the one that has more parameters. The number of parameters, this is 10,000, and the number of parameters here is like 100,000, around 100,000. Okay, so yeah, this is interesting. You can play with this and interact with the visualization. And yeah, there are different analyses here. Okay, so as I was saying, this is very didactic document, and I encourage you to take a look and to read it fully, because I overlooked many things. It was just a very general skin over the document. Okay, so and there are several problems, and definitely the area of research on graph neural networks is very large, and is very active, and they are doing very interesting things. Okay, okay, so for the end part of our session today, we will work on this notebook. You have access to this notebook, and I will work on it as we go today. So I ask you to please open the notebook and follow along what we are doing. Okay, so that you get a better idea of what we are doing, and try to run things. And I think it's more interesting. Exercise is going to be more dynamic. Okay, so this is not complete yet. So I will add things. So every time I add something, I will save it. So if you update your notebook, you will get the updated version. Okay. Okay, so the link to this note, I will post immediately the link here, so that you can follow along. Okay, good, great. Okay, so what's this notebook about? So this notebook is basically we are going to work with a data set. And the task that we are going to work on is a node classification task using graph neural networks. Okay, so we are going to use Keras, two frameworks. We are going to use Keras, and then we are going to use also Spectral, which is an specialized library that works with TensorFlow for doing graph or learning, deep learning over graphs. Okay, okay, good. So here this is initializing. So there is a data set which is a very popular data set. It's a citation data set. I don't know if you already work with this in the course. Is a data set made of a scientific publication, 2,708 scientific publication papers, and they are distributed in 7 different classes. Actually, there is a description here. So these are the 7 classes: case-based, genetic algorithms, neural networks, probabilistic methods, reinforcement learning, rule learning, and theory. These are papers about machine learning, okay? And then we have information about the citations between those papers. There are actually 5,429 links between those papers. And each paper is represented as well by the some vocabulary, the presence of some words, and the vocabulary, the size of the vocabulary is 1,433. Okay. Okay. So here are the references to the relevant papers of this data set. Here we are going to download that data set. It's small, you can download it very quickly. You will see that you will get two uh, files, one with the representation of each one of the papers and one with the information of the links of the graph. So those are the sites. And then, okay, and a README that this one that we have here. So what we are going to do is we are going to use Pandas, which is a framework for dealing with data in Python to load the data set. So here I am loading the citations. And then you can see that is actually here we can visualize it. This is a sample from that data set. So here is like the idea of the paper, and then we have the target and the source. So that means that the paper oh, sorry, this is not, this is just a consecutive number. No, the ID of the paper is this one. So this means that the paper with ID 33303 cited the paper 15600. Okay. So here we have 5,000 of those links. And then we load the information of each one of the papers. So we have 2,700 papers, and each paper has this 1435 attributes, and the attributes are the paper ID, which is here, then 1433 binary values that indicates if a word is present or not, and then the subject of the paper. So here, yeah, we are showing the content. The different fields are here in the vertical. So we have the paper ID, then we have the term 0, the term 1, etc., till the term 1432, and then we have the subject. Okay. Here we do some pre-processing okay, so these are the counts of the paper for each one of the classes, and then here we do some pre-processing to for instance, instead of using the name of the class, we are going to put a number, and instead of doing we are going to have like a consecutive ID for the paper, etc. So that's what we are doing here. Okay, so let's visualize a portion of the graph. Okay, so this is here. So let me copy this. So with this code, we will visualize a portion of the graph. We are only going to visualize 1,500 connections or edges among the papers, okay? So yeah, this takes a little bit. Okay, so now we have the visualization, okay? So you can see here, this is just a portion of our graph, okay? Visualize, okay, just to get an idea. The colors are associated with the labels of the paper. So what you will expect is that papers which are related have more connections between them, okay? But first, what we are going to do is we are going to build a model. So we are going to build a model, a baseline model that is going to ignore the structure of the graph. We are only going to use the information in each one of the papers, okay? So it's a very simple model. these are like the, yeah, let's take a look to the, so here we have some functions to run the experiment, to display the learning curve. Okay, and then this is our model. So yeah, this is our baseline model. Let me, okay. So yeah, so this is a helper function to create a block. This is going to create a number of blocks that have this structure. So you have a dense layer with some pre-processing layers that are that do some kind of regularization. Regularization means operation that makes that control the complexity of your model. Okay, and this is the function that builds our baseline model, and probably it's easier to look at the model here. So basically, you have here, this is a conventional neural network model. This is not a neural network model. It's just a conventional neural network model that use only the information of the papers. It doesn't use the structure of the graph. Okay, so it has 3 blocks, you can see. So here, sorry, it has yeah, several blocks. So it has 1, 2, 3, 4, 5 blocks that are like this here. Okay, and then you can see it received 1433 because remember the number of features or the number of terms that represent each document is 1433, and every layer has 32 nodes. So you can see the different layers, and at the end you have a dense layer that is the output of the model that has 7 neurons. Why 7 neurons? Because we have 7 classes. And in total, our model has a total number of 62,500 parameters. Okay? Okay. So that's our model. This is a graphical depiction of our model. It has something which is usual in neural networks nowadays. Is something called skip connections. So you see that the layers, our model is not sequential. It's have some connection that skips some layers. Okay, and those skip layers basically what they do is they improve, they make the network more easily trainable. Okay, that's what they do basically. Okay, so that's the model. So this is a conventional neural network model, a state-of-the-art neural network model. So it's not a simple model. Okay, then we are going to train it. Train data is not defined. Okay, let me see. Probably I didn't execute something. Yeah, this one. Okay. Okay. Good. And then we are going to run our experiment. Okay. Okay, so yes, please. I don't
Uh,
see who is raising the. Yeah, yeah, please go ahead.
just to make sure that I'm understanding well,
Sure, Ricardo, of course.
the,
That's the
the
idea.
the idea is to make a model to predict the topics,
The
the,
class, yeah.
the
So
class.
we have 7 classes. So these are papers from seven different
Okay.
classes. Some about
Based
neural networks, some about probabilistic methods, genetic algorithms, etc. Okay, so what we want to predict is what's the topic? Yeah, as you said, of the paper, right?
Based on the words,
Only on the words that are present in the
okay,
document.
that's
Okay.
our zero model,
Our baseline model. Yeah,
baseline model,
that's right.
and to
Exactly.
improve it by adding the information of the net of the citation. That's the idea.
That's the idea. So we are going to use a graph neural network that use the citation graph to do the prediction, and we will see if it improves. That's what we expect.
Okay,
Okay.
thank you, thank you, thank
So yeah, that's the idea. So let's see how it performs. So yeah, it's going fast. So we have a train validation. You can see that it is it's already done. Okay, yeah, because here probably we are using patience. Let me see. Yeah. Oh, okay, yeah. Here, yeah. Actually, let's plot the graphs of the training to see what we get. It's easier to look at the learning curves to see how the training process went. Okay. So yeah, let's. So these are our learning curves. So what was going on here? So these are the different iterations, epochs. An epoch is a full pass over the whole training data set. And then we are here, we are plotting both the training loss and the test loss. And we are also plotting the accuracy on the train and test data set. So you see that the accuracy improves like around almost 90%, but in the train data set, but in the test data set, it reaches on maximum probably here around, let me see, how much was that? Yeah, probably around 70 something. Okay, yeah, probably almost 80. No, 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 it didn't reach 80. Okay, and it goes down. Okay, so yeah, probably here it is doing overfitting. So this is like the best it got. And we can evaluate because this is actually training and validation, not tests. And here we can evaluate on the test data set, and we get an accuracy of 73%. Okay,
To share me,
73%
how do you
using a
define
yes.
the training data, the number of training?
Oh, yeah, here, basically, yeah, let me go back to it. Yeah, I didn't talk much about that, but really what we did here was to partition the data set more or less in half for training, half for test. Remember that this is only one graph. Then our instances here are the nodes of that graph, the papers. Okay, so we use half of the nodes for doing the training, and we keep half of those nodes for doing testing. Okay.
Okay, the question is more related. How do you define correctly from half to training, half to
No,
uh,
no, that's arbitrary. That's actually
okay.
no, that's arbitrary. Uh, yeah, actually, if we go to the original to the papers that use this, typically they use less for testing. Okay, it depends. It depends. For instance, in the original paper of the model that we are going to use here, yeah, actually, we can go to the paper. We can look at that. Yeah, actually, I have a link to the paper. Yeah, probably paper is here. This is one of the classical papers. It's called Semi-Supervised Classification with Graph Convolutional Networks. So in this paper, yeah, I come back to this. But in this paper, they use this same data set. Is the Cora data set. This is the one that we are using. Okay. And label rate means since the purpose here was to show that just with some small number of labels, you may have a good prediction for the full graph. They use only for training the 5%, not 50%, but the 5%. Okay, in this paper, and actually they get pretty good results. For Cora, they get around 81%. Okay, so yeah, it depends on what you want to do. No, in this particular paper, the purpose was to show that just with some small number of labels in your notes, you can predict the rest. Okay.
Okay, thank you, teacher.
Yeah, but it depends on what was the purpose of your experiment. Okay, good. So, mm, yeah, so the learning, okay, so the accuracy here is 73%. So now we are going to use another, yeah, let me copy this because I need to install some things. Um, Okay, we are going to use a software which is called Spectral. Okay, it's a framework. Yeah, give me a moment. We'll go right away to Spectral. Okay, so yeah, let me run this so that we have to install it because it's not installed by default. So we installed with this instruction. So what's a Spectral? Let me open this. So a Spectral is a Python library that uses Keras and TensorFlow to do graph deep learning. Okay, so that's what the Spectral does. Okay, Spectral, yeah, actually, let me go here to see how they deal with the main challenge of building a framework for doing deep learning over graphs is dealing with the different kinds of tasks, learning tasks that you may have in a graph. Okay, so something which is central to any of these frameworks is that you need a representation for a graph. So they have a class to represent a graph. Okay, so what's a graph? Then you have the node features, you have the adjacency matrix, you have attributes for the edges, and then you have labels for the nodes. It is possible, but for some graphs, you don't have any of these. Typically, the least you may have is the adjacency matrix, okay? Um, but for instance, in our case, we have no features. We have of course, the adjacency matrix, and then we don't have edge attributes, and we have no labels. Okay, so the graph. Now, this is to represent an individual graph. Spectral also have the concept of a data set. So a data set is a set of graphs. Okay, so depending on the task, you may have different data sets, types of data sets, and they have something which is called data loaders. Okay, and that's very important because there are different ways to deal with the data and different ways to show the data to your uh, uh, model. So they have something they call a single loader, a disjoint loader, etc. And actually, let me see. I will not go into the details, at least not today. Uh, uh, but just to illustrate the complexity of dealing with graphs, see, these are the different modes that you have to represent the different tasks. So the single, disjoint, batch meets, and the shapes of the adjacency matrix, the shape of the attributes for the nodes, and the shapes of the attributes for the edges, and you see that they change according to the mode that you use. Okay. So actually, what we are going to do here is something very simple. We are going to use like a single mode. So it's like the easiest way. And yeah, let's see directly on the code, okay? Okay, so here I load the spectral. Then what I do here is to create a class to represent my data set. Okay, so first, from the data that you already saw, I have the adjacency matrix. Okay, so this is a NumPy matrix. This matrix that we are using here is an sparse matrix because typically adjacency matrices are sparse. Sparse means that they are full of zeros. The most of the entries in the matrix are zeros. So we don't want to represent those zeros. We just represent those numbers which are different to zeros. So that's why we use a sparse matrix. And then we are putting the information, the source and the target. Remember, those are the links or the edges on my and this is undirected graph. So I'm using if there is a citation from source to target, I put a one, but also I put a one from target to source. Okay. And then I have the labels, and here this class is representing my data set. My data set only has one graph. So this is a very simple class to represent a data set. This is the constructor of the class that specify like the number of features, the changes symmetry, the labels. And then there is a method read that is the method that is called by Keras or TensorFlow when it's training. And the only thing that I do in read is create a graph and return that individual graph. So it's very simple what I have here, okay? Is a data set that only has one graph. Okay. Here there is a challenge again. That's why I find, okay, I should have been done a disclaimer at the beginning of the class. The disclaimer was that I'm not expert on a graph neural networks. Actually, one motivation for being involved in this class with Professor Alfonso and Professor Luis Fernando was to learn about graphs because, yeah, I knew some things, but really, I'm learning this semester about network science. I mean, with all the details and all the nice work that Professor Alfonso and Professor Luis Fernando have done. And I didn't know before this about graph neural networks. So I learned about graph neural networks to teach this class. Okay. Okay. So something that I found very interesting about graph neural networks is that it's really challenging to things that are very easy to do with conventional data with graphs is more complex. For instance, I have this network, and I have only this network, right? And this is my, and then I have to classify the nodes. So how do I tell to my model which part of the nodes are training, which part of the nodes are validation, and which part of the nodes are for test? If I only have one graph that represents my network. So the way to do it in a spectral is using something which is called masks. Okay, so let me show you here. Basically, here, what I'm doing here is defining mask. So what's a mask? Yeah, let's look at a mask. Okay, so for instance, I have here a mask for training, a mask for validation, and a mask for test. So what's the mask? It's basically a vector. Yeah, let me print here. So for instance, the train mask. So let's see the shape. So the shape is oh, sorry. The dimensions. So it's a vector of 2708 positions. So this is the number of nodes in my graph. Okay. And the same thing for the test, and the same thing for validation. Okay. Yeah, we can look at them. Validation and test. Okay, so all of them are vectors. Okay, and they are vectors with zeros and ones. Okay, so let me print here the first position of the train mask. Let's print 20 positions. And also let's print 20 positions of the test mask of the evaluation mask. So yeah, these are the first 20 positions. So see, for each node, so for instance, the node 0 is in my validation data set, you see? And the node 1 is in the test data set. The node 2 also in the test data set, etc., etc. For instance, yeah, here in this, I don't have nodes in the training data set. Okay. All of them are in the either in validation or testing. But if I go, I don't know, let's see, from 2000 to 2020. So the way to specify which nodes we are going to use in this task for each part is using mask. Okay, so that's what I am doing here. I use those masks to do something which is called okay, as I was saying, we are going to use a single loader, and the single loader receives something which is called sample weights, because I can give to weights how important a sample is going to be. So actually what I'm doing is giving a sample weight of 0 to those samples that I'm going to ignore, and a sample weight of 1 divided by the number of samples or for that training set, for that subset, for those nodes I will going to use. Okay, so I define 3 loaders: one for the training, one for testing, and one for validation. Okay, okay, and then I define my model. It happens that here our model is absolutely simple. I don't know if you can see where I am defining my model here. Anybody can identify in where in this code I am defining my model?
In line 8.
Exactly. So that's what I'm doing. I am using a predefined model provided by Spectral. So here in Spectral, if we go to models, uh, is the first one, and is the one from this paper, the paper we were discussing, is a graph convolutional network. Okay. And then basically I am specifying only one argument. The argument is the number of labels, and that's it. The other parameters are by default, and you can read about the details of the model. It has two layers of graph convolutions. And then, yeah, actually here, graph convolution looks something similar to this. This is the paper, the original paper. And a graph convolution looks something like this. It's basically a layer that integrates the information of the node, something as we saw in the tutorial. Okay, so each node in a graph convolutional layer, the representation of a node is modified doing an average of the nodes which are neighbors and applying some transformation. So that's a graph convolutional layer. And the model that we are using is a model that has two convolutional layers, and that's it. And the other parameters are by default, okay? And then we compile it, and we specify the loss is a categorical cross entropy because we have several categories. And then here we are going to train it. Okay, and let's see what happened. And here, let me copy the code for. Yeah, see that here I'm not using GPU because it's a small model. Okay, and it's enough to use CPU to do the training. So yeah, this is going to do around 200 iterations. So just to remember, let's go out while ends, what is the performance that we obtained only using the information of the nodes? 73%, 73%, okay? 73%. Yeah, kind of. Ricardo said that it's like moving average in ARIMA models. Yeah, that's right. Yeah, a moving average is like an average through time. Here, the average is like a spatial average using the information of the graphs. Yeah, that's right. That's a good analogy. Okay, so 73%. Let's see what performance we obtain. This already ended. Good. These are the learning curves. And this is the performance. What happened? Yeah, these are the learning curves. Okay, and see the performance. So the performance is 82%. Okay, compared with 73%. So we have like an improvement of 9 percentage points, 9 percentage points. So that's good. So that's good. That's a good improvement. And really what's going on here is that integrating the information of the network, it really helps to this task. Okay. Okay, we are almost at the end of the class. So any questions? I know you are tired. Any questions, comments?
Uh,
Yes, yes, go ahead. Open your mic.
I'm sorry, I got a question, but it's about the about the video.
Mhm.
I was when I was trying to reproduce it.
Uh-huh.
There there was a part that I could not do. The magic thing. Sorry, I the
Oh, you mean in the but the you mean the Keras, the video of the Keras example, right?
yes, the tensor both magic function. I
Oh,
It doesn't work or
okay. Probably there was an update and it's not working in the way that is in the notebook. So yeah, probably yeah. I'll check that and I'll update it. Yeah, the thing with this that's a problem, you know, that libraries are changing constantly. So there is a problem of reproducibility in general because of that. Because is the code that was working stops to work because the versions of the library change and all that. So yeah, that probably that's the case. So we have to date it, but for
okay.
sure there is a way to do it with the new versions. Okay. Yeah, I look at that and I solve it. Okay. Okay. Any other question or comment? Okay. So thank you very much for your attention, guys. Oh, okay. Yes, Edgar.
Yes, teacher. I want to ask about the trade-off between, I mean, we are increasing 9% here,
Mm-hmm,
but we have a very complex model,
mm-hmm.
a more complex model. So what's the trade-off between the improvement percentage and the computational capability of the that is required to train such a model?
Yeah,
Now,
actually, yeah, it depends how you measure the complexity. By the way, that's good question. So let's see if we can print the. I'm not sure if we can print the parameters of the. Let me see. Here we call the. So one way to measure the complexity is according to the number of parameters. Okay, of our yeah model is the name model summary. No, this works. Yes. See, trainable parameters, 23,000. Okay. And our previous model, I think, had more than that. So here, our previous model has 59,000. So from that point of view, actually the graph neural network model is simpler. Okay. So from that point of view, the number of parameters, that model is simpler and is more powerful. However, from a conceptual point of view, yeah, probably this is a more complex model conceptually, you know? So yeah, that's something that you have to take into account. I don't know when you were thinking about complexity, which one of which type of complexity were you thinking about?
Yes, that this was one. Effectively, the
You
graph
know,
is smaller, so
yeah,
less complex. But I guess
yeah,
when we have a bigger models, we need bigger or we need larger
hmm,
capabilities on the system that we are using to train the model.
hmm.
So, what's the trade-off? That's something that is
Yeah,
I'm curious
yeah.
about.
The common sense 20 years ago said in machine learning that the smaller the model, the better, because you were less prone to overfit, for instance. But that was 20 years ago. Nowadays, the wisdom is different. Actually, the experience has shown that even with models which have millions of parameters, you may get good generalization. So, yeah, in the case of neural networks, probably the number of the size of the model doesn't matter that much. Because there is an important trade-off between complexity and simplicity that has to do with interpretability, but in general, neural networks are not interpretable. I mean, you can make them interpretable by default, they are not interpretable. So you don't have that trade-off with neural networks. So usually, what you care about is if your model is how costly is to train your model, how costly is to predict. For instance, if you want to put this model in your cell phone, something that you have to think about is how much energy does it consume. So probably you prefer a smaller model, but there are techniques. For instance, there is something called distillation that takes a model which is large and then makes like a smaller version of the model that is more efficient, consumes less energy, and the sacrifice on performance is less. So yeah, that's the kind of things that you have to look at. Interpretability is another one. However, typically neural networks are not interpretable. So the trade-off is with other kind of models. But yeah, always there is a cost that you pay, right? But I don't know if that answers your question.
Yes, thank you, Professor. But you bring another topic that I would like to ask, and that's about the interpretability of the
Right,
models. So
right.
how can we assess that? And you say that there are some techniques.
Yes. Yeah, that's yeah. For instance, in the case of the images, there is a good amount of work trying to say, okay, if a model classify an image or identify an object in an image, can the model tell me why or what was? So yeah, there are techniques that allow you, for instance, to show which part of the image were more important for the decision. Use kind of attention, which is other mechanism to show that. For graphs, I'm not aware of about that, but I guess that one of the some of those techniques may be extended to a graph. For instance, if I have a task at the level of the graph, it will be interesting to know if it's classifying the graph, for instance, a molecule, to know which parts of the molecules are like those which are more important for the decision. And I guess some of those techniques can be extended. But in general, interpretability is a topic that is really researched a lot because there is a lot to do. And in general, these models are not interpretable. Okay. Luis Alfonso.
Thanks, Professor.
Yes, I have a question about the training time. I have in mind something that I'm not sure if it's wrong or not, but I am thinking that for these networks, the training time depends on the network architecture, because normally on a deep neural network, a conventional one, the gradient descent we do is just one pass from the output to the inputs, but in this case we have to do one pass for each node with all its neighbors. And I can imagine a neural network with a high clustering coefficient, then we would have to do a lot of passes of gradient descent from each node to each of its neighbors, making it
Yeah,
slow.
that's good questions. You know, when I was reading, thinking about the architecture of these neural networks or graph neural network without reading that much. At the beginning, yeah, I was thinking about that the problem of the efficiency of implementing this, but actually the implementations are very clever. Okay, so actually the cost is not that much. Actually, there is no like uh, 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 kind of yeah, but because you may think that the information has to flow from one place to another place. Actually, this is a good illustration of what happens. Yeah, this was yeah. Let me go back to this just to illustrate what's going on. Yeah, I forgot because this is at the beginning, but it doesn't make much sense when you haven't discussed. This is what happens in a graph convolutional network. Okay, so see, this node in the next layer is going to be connected to the neurons. Or okay, so here you have like a neuron for each node. So this node here is connected, you see, to the nodes in the which are neighbors in the graph, you see. But since these are connected, for instance, this node is connected also to the nodes which are neighbors in the graph. But it means that, for instance, this in the layer, this node that I'm highlighting here in the layer 1 is only connected to two nodes. But in the layer 2 is connected to more nodes, and layer 3 to more nodes. So really what happens is that in these networks, the information flows like it flows in any conventional neural network. And the connectivity from nodes which are far apart in the graph is accomplished thanks to the multiple layers that the neural network has. Okay, so really it's not a problem. And actually all these connections as the spark connections are implemented in a very efficient way. So actually that's not a problem, and this works pretty much as any other neural network. Luis.
Okay, thank you. That clarified my question. I think that image really helped me understand it. I had the wrong idea.
Yeah, this document is really very good, and this interactivity you helps a lot to understand. Okay, any other comment? Okay, it's already 9. So thank you very much for all your attention, and we'll see again. I think in 2 weeks we will have an additional session that probably we are going to do like a kind of work on something practical, and you will work on that. Okay, thank you very much. Have a good night.
Good evening.
Thank you, teacher Fabio.
Thank you.
Thank you.
Professor, can you stop the recording, please? Professor Fabio?
Sure.
Thank you.